All right, so this is 3.1 video 2. So we've been talking about the idea of absolute and relative maximums and minimums. Now that we kind of have an idea what those are and how to find them, we're going to talk about this thing which is called the extreme value theorem. Okay, kind of is exactly what it says. We're talking about extreme values, so we're talking about maximums and minimums. It's a theorem that deals with that. And here's what it says. It says, if f is continuous, wow, let me try and write that so it actually looks like the word continuous. If f is continuous on a closed interval, meaning that the endpoints are included, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some number, c and d, in the closed interval a to b. Okay, it might not make a whole heck of a lot of sense, but really this is all it says. If you have a continuous and closed function, you have to attain an absolute maximum, highest point, and an absolute minimum, lowest point, someplace in between the endpoints. Okay, that has to happen. So for a frame of reference, let's show two examples where this doesn't actually hold. So let's take a look at, let's say we've got an a over here and a b over here, and let's say our function might look something like this. Got something that does this, goes up to here, and then comes down to here, somewhere in there, something like that. So what you should be able to see here is that this is a closed interval between a and b because the endpoints are included. The biggest thing here is it's not continuous. So the extreme value theorem is not going to hold here necessarily. It doesn't mean that you might not have an absolute maximum and absolute minimum, but the extreme value theorem won't guarantee it. Now in this case, we actually do have an absolute minimum. That seems to occur maybe at a. So you would have a lowest possible value on this graph. It looks like you would have it at a, so f of a would be the lowest possible value. However, there is no absolute maximum because where the absolute maximum would occur would probably be like right there, but this thing is going to approach a y value up there, but it will never get there. So technically there is no highest possible value. It's going to approach a value, but it will never actually get to it. So in this case, there would actually be no absolute maximum. Pen stopped working. Oh, there we go. Looks like we got the pen back. Okay, one more example. So once again, we'll do, we'll put a over here, and we'll put b over here. And this time, we'll make the function look something like this. Whoops, definitely did not draw that right. There we go. And we'll say that we have a vertical asymptote there at b. So it's definitely a continuous function. Doesn't ever look like it's going to stop, and it won't. But what it is not closed, because this thing will never actually get to b, so it's not a closed function. Again, it looks like it has an absolute minimum someplace down there in between a and b. It's just not guaranteed by the extreme value theorem. And again, there's no absolute maximum because this thing just goes on forever. Okay, so let's go ahead and look at a couple more theorems. Now, these are going to be extremely important. At the minimums and maximums on these particular functions, the tangent line is either one of two things. It's either horizontal, which you saw in that first graph that we did our absolute and relative maximums you would have a horizontal tangent line if you were to look at those where they're kind of curved at the top, or, excuse me, not or. So at those places, the slope would be 0. And then we've got this thing which is called Vermonts Theorem. It's actually not something you have to know by name. You don't need to know Vermonts Theorem by name, but you definitely need to know what it says. So if f has a local maximum or a minimum at C, and if f prime exists, that's important, then f prime of C is going to be 0. Now think about what that says. If the derivative exists, and you have a local maximum or minimum. So basically it means you have some kind of a, like this or like this, then right here at the top, the derivative is going, or the bottom, the derivative is going to be 0. Okay, it does not hold true if it's like this, because the derivative does not exist right there. You will still have a max or minimum there, but you would not have a derivative which existed. What we call those places at the top or the bottom of those hills where something is happening, something very important, it is called a critical number. It's called a critical number of a function f. So the critical number of a function is a number c in the domain, remember c is an x value, of f, such that either one of two things is true. Either f prime of c is 0, or f prime of c is undefined. And that's what we have going on here. These kind of places would be where the derivative equals 0. This would be where the derivative doesn't exist. That is called a critical number. Okay, right there, or right there, or right at the top. Those are critical numbers. So if you want to find a critical number, you'll end up taking a derivative. You'll set the derivative equal to 0, or you'll see where it's undefined, and that will be your critical number. Okay, so if f has a local maximum or a minimum at C, then C is called a critical number. Okay, so what it's saying is, if you know that you have a maximum or minimum at C, then you're going to have a critical number. That's it. All right, so let's go ahead and take a look at an example of how we're actually going to use this extreme value theorem. Actually, I'm sorry, no, we have one more definition to do first. We have what's called the closed interval method. This just kind of tells us how to do it. The closed interval method says, to find the absolute maximum or minimum of a continuous function, we can use the extreme value theorem on a closed interval from A to B. You're going to do these following things. You're going to find the critical values. Find the values of f at the critical values. Then you're going to find the values at the endpoints. Really simple. The critical values are basically going to be locations of potential local maxes and mins. The endpoints could be possible absolutes, as well as the critical values could also be absolutes. But basically, you just need to check all the critical values and your endpoints. Whatever the highest value is from steps 1 and 2 is the absolute maximum. Likewise, the lowest of those values is the absolute minimum. And that's it. So let's go ahead and do an example. Okay, so example 2 says find the absolute maximum and minimum values of the function. In order to find the absolute maximum and minimum values of the function, we need to find the critical values first. To do that, we take the derivative. So we'll do f prime of x, and that's just going to be 3x squared minus 6x. Now we have to find the critical values. The critical values are where the derivative is either 0 or undefined. Well, it's a polynomial, so it's never going to be undefined, but we can certainly figure out where it's equal to 0. So we'll go ahead and factor a 3x out of there, and that'll leave us with x minus 2. So we're going to get that the polynomial, the function has critical values at x equals 0 or at x equals 2. So in order to find where the absolute maximum and minimums are, it's either going to be at 0 and 2 or at the endpoint. So the easiest thing to do here is just to set up a chart. We'll put our x values here, we'll put our function values here, and we'll evaluate. We're going to evaluate them at 0 and 2 because those are the critical values, and at -1/2 and at 4. Now I do want the f of x values, I want the function values, so we plug these back into the original function, f of x. So plugging 0 in, that's the easy one. That's just going to give us 1. If we plug in 2, that's going to be, let's see, what is that going to be? 2 cubed is 8 minus 3 times 4, so 8 minus 12 is -4 plus 1 is -3. We still have to plug in the endpoints. 4 is going to be a little bit bigger, so 4 cubed is 64 minus 3 times 16. 3 times 16 is 48, so 64 minus 48 is 16 plus 1 more 17. The -1/2 is going to be a little bit more challenging. That's why I kind of saved that one. You can actually do that one. If you can't do it in your head, which is fine, go ahead and write it down, but you should definitely practice doing this without a calculator because you would be expected to be able to do this without a calculator on a problem, something like this on a test. But it does work out to be 1/8. So really all you have to do is look at, okay, what's the biggest number here in my f of x? Well, it's 17. Whoops. There we go. It's 17. What's the smallest number? -3. There's your absolute maximum and absolute minimum value. So we'll simply write that the absolute max is 17 and the absolute min is -3. And that's the general concept between absolute max and absolute min. Okay, let's go ahead and put this into more of an application. Same idea. And we're going to assume that we're not going to be able to use a calculator on this stuff. So even though it says use a graphing calculator to estimate, we are not going to do that part. We are not going to use a graphing calculator to estimate those things. We are going to use calculus to find the exact max and the exact minimum. All right, so we are given a function, f of x equals x minus 2 sine of x from 0 to 2 pi, so it's continuous, it's closed. We can use the extreme value theorem, which says we're going to take a derivative, which is going to be 1 minus 2 cosine of x. Again, that is not something which will ever be undefined, so we're going to set it equal to 0 and solve this for x. Finding critical values. So let's see, if we subtract 1 and divide by -2, you're going to get that cosine of x is 1/2, which means, going back to our circle stuff, that x would have to be at the pi thirds. And it's going to be positive in first and fourth quadrant, so that's going to be 5 pi thirds as well. So there's your critical values because we're only going from 0 to 2 pi. So now we have to go ahead and set up our chart. So here is the x, here is the f of x. So let's see, our x values are going to be at pi thirds, 5 pi thirds, and we have to check our endpoints of 0 and 2 pi. The 0 and the 2 pi are likely to be the easiest ones to check, so let's go ahead and start with those. If we plug 0 and 2 pi back into the original, remember we're going into this one, plugging 0 in for x is nice because 0 minus 0 is 0. Sine of 0 is 0, so that works out nicely. Plugging in 2 pi, well, sine of 2 pi is also 0, but don't forget you're plugging 2 pi back into here. So it's 2 pi minus 0, which is still 2 pi. Now, we're going to have to do some actual estimating here for pi thirds. and 5 pi thirds, because if you plug in pi thirds, what we're going to get here is pi thirds minus 2 times the sine of pi thirds. Sine of pi thirds is root 3 over 2. Times 2 is just going to be root 3. And then 5 pi thirds is going to be 5 pi thirds for x minus 2 times the sine of 5 pi thirds. That's fourth quadrant, so that's going to be positive. Well, it's going to be negative, but the minus minus makes it positive, root 3 over 2. So again, it's going to be root 3. So now the real question is, what's going to be the bigger and smaller value? So we have to do a little bit of estimation here, because this could be negative. Okay, it could be less than 0. Otherwise, 0 is definitely going to be our smallest. And this one right here could be bigger than 2 pi. But again, here's where our estimation techniques are going to have to come into play. So you do have to kind of know something about root 3. That's approximately 1.7. So root 3 is approximately 1.7 or so. And pi over 3, well, pi is about 3.14. So if you divide 3.14 by 3, you're going to get a number which is just a little bit bigger than 1, but definitely not near 1.7. So we're going to get a number which is just a little bit bigger than 1 minus 1.7. That's going to give us a negative value. So this is definitely going to be your minimum, because that's going to be negative. And then we've got to do the same general idea for the 5 pi thirds plus root 3 and the 2 pi. 2 pi is about 6.14, so that much we know. So that's approximately 6.1. I'm sorry, 6.28. Got to double it. So that's approximately 6.28. This is awful. There we go. So the 5 pi thirds is going to be something plus the 1.7. So let's see. 5 pi, again, 3.14 or so times 5 is going to be 15.7 or so. And 15.7 divided by 3 is going to be 5.2 something. 5.2 something. 5.2 something plus 1.7 something is going to be 6.9, which is definitely greater than the 6.8. Again, these are all just estimations. This is not exact values here. We don't need the exact values because that's given to us. But this means this is our maximum. So we'll go ahead and write that out. The absolute max and the absolute min. So the absolute maximum is 5 pi thirds plus root 3. And the absolute minimum is our pi thirds minus root 3. And those are exact values. Obviously, if you're allowed to have a calculator, you can plug these things in. It would have been much easier. But I want to get you used to doing some estimation techniques, just in case you're not allowed to have a calculator on some of these types of problems. Okay, one more example to go. And it says, the Hubble Space Telescope was deployed on April 24th, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during the mission from liftoff at t=0 until the solid rocket boosters were jettisoned at t=126 seconds is given by that really messy velocity function right there. In feet per second. Using this model, estimate the absolute maximum and minimum values of the velocity of the shuttle between the liftoff and the jettisoning of the boosters. So we want the absolute maximum and minimum of the velocity. Well, they gave us the velocity, so we're going to need to take a derivative. V prime of t. Now this is obviously a little messy, so you could use a calculator on this one, and I've already done that. So it looks like the velocity is going to be 0.003906 t squared minus 0.18058 t plus 23.61. And we should also know that this happens to also be the acceleration, because that's the derivative of velocity. We do need to figure out where that's going to be equal to 0, because we need the critical values. This is not something which I would expect that you would be able to do. Obviously, you could try and use a quadratic formula, but this is really messy numbers. So plug this into your calculator and see where this velocity or the derivative here would equal 0. When you do that, and again, be careful what you're looking at, when you do that, you should notice that this thing never actually goes below the x-axis, meaning there are no critical values when you plug this in. You will not get any zeros for that derivative function. That means that the only possible places you could have an absolute max and an absolute min are at the endpoints. And they have given us the endpoints as t equals 0 and t equals 126. So this is actually kind of cool. We plug 0 in, that's really easy because you plug 0 into your velocity, the first two terms go away. It's 23.61, and it's going to be, shouldn't be, sorry, that's wrong. I got to plug in the velocity, not the derivative. That's going to be, was it negative 3.083? Negative 3.083 meters per second. And then if we plug in 126, much bigger number to deal with, that's going to be 4,142.822. I said meters per second, I meant feet per second. Feet per second. Now, why do I think that this stuff is cool? Well, to me, it's kind of cool. I'd like this, enjoy this kind of stuff. But think about what happens here. If you've ever actually watched one of those launches of a space shuttle or something like that, and you really get a real close-up, when those clamps come off of the space shuttle, what you notice is the space shuttle actually starts to fall for a very, very short amount of time. That's that negative velocity at time t equals 0. It's actually going back towards the ground before the boosters and stuff actually start to lift it off the ground. Pretty cool. That's why that's a negative 3.083 feet per second. And the other thing that's really cool is the fact that when it gets to the point where the boosters are jettisoned, a little over 2 minutes into the thing, because it's 126 seconds, it's going at 4,142 or so feet per second. There's a little over 5,000 feet in a mile. So this thing is moving almost 1 mile per second. That's actually kind of cool. That's really fast. Anyway, that's just kind of an aside. That's how you would do the problem. Plenty enough for these videos.